Hello students, welcome to Gnanataranga CET coaching classes organized by Government of Karnataka in association with Pre-University Education. I am C.V. Reddy, lecturer in chemistry. So today we are going to discuss about the chemical bonding and molecular structure. After the completion of that, we can have some idea regarding states of matter. Then we can consider some points about redox reactions also. See, if we consider the chemical bonding and also molecular structure, in which we are going to discuss about chemical bond, types of chemical bonds, ionic bond, covalent bond, coordinate bond, hydrogen bond, lattice energy, types of covalent bonds, that is sigma and pi, then hybridization, VSCPR theory and also molecular orbital theory. Now let us consider the chemical bonding. What is chemical bonding? The study of chemical bonds is known to be chemical bonding, in which what is a chemical bond? The force of attraction between two atoms or between two ions or between two molecules is known to be the chemical bond. That is, for example, if we consider between two atoms, hydrogen and also hydrogen, between two ions, that is Na plus and also Cl minus, and also between two molecules, that is, for example, you can consider NH3 and also BF3. Okay, like this. Even one more bond may also be considered, that is known to be the metallic bond. However, we are not discussing metallic bond in this chapter. Let us concentrate on these concepts only here. That is, to begin with, let us have an idea about the ionic bond here. That is, suppose if we consider ionic bond. What is ionic bond? The force of attraction between two oppositely charged ions is called as ionic bond. Two oppositely charged ions, that is, suppose if we take up sodium and also chlorine, ionic bond is usually formed between the alkali metals, lithium, sodium, potassium, rubidium, cesium and francium. They are called alkali metals. And then even we can consider alkali earth metals like beryllium, magnesium, calcium, strontium, barium and also radium, and with halogens. Halogens, they are the salt forming compounds. Halogens, they may be fluorine, chlorine, bromine and also iodine, and even astatine is also an halogen, but we cannot expect the formation of bond between astatine and also any of these alkali or alkali earth metals. Now let us consider the most interesting point with respect to the formation of the ionic bond here. You consider the formation of sodium chloride. In case of sodium chloride, you consider sodium, atomic number 11, electronic configuration is 1s2, so 2s2 and 2p6, 3s1. That is, sodium contains one electron in the outermost orbit. And whereas, suppose if we consider chlorine atom, that is atomic number 17, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Now in this case, sodium contains one electron in the outermost orbit, whereas chlorine contains 7 electrons in the outermost orbit. So sodium can lose one electron and chlorine can take up that electron. That is, after losing the electron, sodium acquires a stable noble gas configuration of neon. That is, it consisting of 10 electrons. So it is 1s2, 2s2, 2p6. That is the noble gas configuration of neon. Okay. That is, in the formation of ionic bond, after losing the electron, the element acquires the stable noble gas configuration of preceding element. The preceding element is neon. And whereas, suppose if we take up the chlorine atom acquires a stable noble gas configuration of succeeding element, that is after taking up the electron, the total number of electrons should become 18 here. So, it will be 18 acquires stable gas, noble gas configuration of argon. That is a succeeding element. See here, preceding element is neon and succeeding element is argon. That means totally, you remember very one important point here, that is any in the formation of ionic bond, one of the atom loses electron, other atom gains electron, atom losing the electron acquires the noble gas configuration of preceding element, and atom gaining the electron acquires the noble gas configuration of succeeding element, and it may be represented as plus and minus. That is you can consider event like this: sodium with one electron, that is in the outermost orbit, and whereas chlorine, it is 1s2, 2s2, 2p6, 3s2, 3p5. This 3p5 consisting of 3px2, 3py2, 3pz1. That is it contains 3s2. This is one pair of electrons, another pair of electrons, one more pair of electrons, and one electron. Now sodium is donating that electron. Now it gives actually Na, okay, which may be represented like this, Cl, okay. Totally chlorine is given negative charge, sodium is given the positive charge. That is with respect a brief idea about the ionic bond. And now let us consider the next one, that is known to be the covalent bond. In case of covalent bond, see, it is very simple. Covalent bond, that is a covalent bond. Now what is covalent bond? Very simple, you have studied it many times. Covalent bond, it is the chemical bond formed by the sharing of a pair of electrons between two atoms in a molecule. That is you consider hydrogen, atomic number 1, electronic configuration 1s1. Suppose if you consider two hydrogens, it is 1s1 again. Now you consider the formation of covalent bond between two hydrogen atoms, that is 1 plus 1. So totally you can write the sharing of electrons between two atoms. That is in totally a single bond is formed by the sharing of one pair of electrons, and a double bond is formed by the sharing of two pairs of electrons like this, and a triple bond is formed by the sharing of three pairs of electrons, 1, 2, 3. This is the formation of triple bond with reference to the covalent bond it is. Now suppose if we consider the coordinate bond. What is coordinate bond? Coordinate bond means here, to consider the coordinate bond, we have to know what is the lone pair of electrons. What is called lone pair of electrons? Let us know lone pair of electrons. If you want to discuss about coordinate bond, lone pair of electrons. Lone pair of electrons means here a pair of electrons present in the outermost orbit but not involved in the formation of either ionic or covalent bond is known to be lone pair of electrons. That is suppose if we consider the lone pair of electrons in case of nitrogen, it is atomic number 7. Sometimes in the exam they will ask questions based on this also. How many lone pair of electrons are present in nitrogen and how many lone pair of electrons are present in oxygen, like that also. Or as fluorine, or as even neon also. That is 7. It may be written like this: 1s2, 2s2, 2p3. Now the outermost orbit 2s2. According to Hund's rule, you can write it as 2px1, 2py1, 2pz1. So here it is like this, one pair, and this is 3 electrons, 1, 2, 3 electrons. So totally the nitrogen contains one lone pair of electrons. This is the lone pair of electrons present in nitrogen atom. and here these 3 are unpaired electrons, they can form covalent bonds. That means totally sometimes they will ask questions, that is how many lone pairs of electrons are present in some elements like nitrogen, fluorine, like that. For that what you can remember is you consider 15th group elements, then 16th, then 17th and also 18th group elements. It is Np square b, that is nitrogen, phosphorus, arsenic, antimony and also bismuth. Np a square b, Np a square b. Then 16th group elements, O s square, oxygen, sulfur, selenium, tellurium and also polonium. And then 17th group elements, that is fluorine, chlorine, bromine, iodine and also astatine. Here 18th group elements, except helium, it is neon, argon, krypton, xenon, radon. You can remember like this, one lone pair of electrons is present in 15th group elements, one lone pair, 1. 2 lone pairs are present in 16th group elements, and 3 lone pairs are present in 17th group elements, 3 lone pairs, and 4 lone pairs of electrons are present in inert gases. In general, you can remember this is also one of the most important point. With this background, let us know what is called the coordinate bond here. Coordinate bond means it is a chemical bond formed by the transfer of both the electrons from one atom to other atom. That is, you consider the formation of covalent coordinate bond. It is also called as dative bond between ammonia and also boron trifluoride, in which it is like this, nitrogen. Just now I have written nitrogen contains 3 unpaired electrons. These 3 unpaired electrons can form 3 covalent bonds with the 3 hydrogen atoms. This is ammonia, and it contains 1 lone pair of electrons, whereas it is boron trifluoride. Now ammonia is a electron rich species, also called as Lewis base. Boron trifluoride is electron deficient species, also called as Lewis acid. Okay. Now it donates a pair of electrons. This is actually bond between the 2 molecules, so which may be written like this, NH3, okay, then it is a BF3, that is called an adduct. Adduct means addition compound. Ammonia boron trifluoride, NH3 and then BF3. That is, in total you remember, generally ionic bond is represented with plus and minus sign as, and covalent bond like this, and coordinate bond is represented like this with an arrow mark. Coordinate bond is represented with an arrow mark. Okay. Now that is a coordinate bond. Now you consider the next one, that is a hydrogen bond. Many questions are asked based on the hydrogen bond in the previous CET examination and even in the NEET examination also. That is, we take up hydrogen bond, hydrogen bond, hydrogen bond. What is hydrogen bond? It is the force of attraction between hydrogen atom and the more electronegative element. The force of attraction between the hydrogen atom and the more electronegative element is called as the hydrogen bond. That is, more electronegative element means it may be like oxygen, nitrogen, fluorine, like this. Let us consider 1 or 2 important applications with respect to the hydrogen bond and also types of hydrogen bonds. How many types of hydrogen bonds are there? There are 2 types of hydrogen bonds. One is called as intermolecular hydrogen bond. Intermolecular hydrogen bond. That is intermolecular hydrogen bond. Okay. That is intermolecular hydrogen bond means the hydrogen bond formed between two molecules of the same substance is called as intermolecular hydrogen bonding. That is, you consider example water and also ammonia. Let us consider water here. In case of water, the hydrogen atom of one water molecule is linked to the oxygen atom of other water molecule through intermolecular hydrogen bonding. It is like this: H O H, H O H, H O H. See, oxygen atom of one water molecule is linked to hydrogen atom of other water molecule through intermolecular hydrogen bonding. Now, due to intermolecular hydrogen bonding, water has high boiling point, and water has very high boiling point due to intermolecular hydrogen bonding, and it is existing as a liquid. Whereas if we consider hydrogen sulfide, see, oxygen and sulfur belongs to the same group, but in case of hydrogen sulfide, hydrogen bonding is not possible because hydrogen atom is linked to the less electronegative sulfur atom. Hence why hydrogen sulfide is existing as a gas, and whereas water is existing as a liquid. That is one important point. And the second point is, in case of water, in case of ice, if we take up water and also ice here, ice always floats on water. Ice always floats on water. Why? Because the density of ice is less compared to the density of water. Why ice has less density compared to water? Because in case of ice, see, due to hydrogen bonding, each oxygen atom is tetrahedrally surrounded by 4 bonds, that is, which I can represent like this: H, so O, H, okay. Now it is like this: H, O, H I am considering, see, and here it is like this: H, O, H, again it is H, O, H. Observe it now. In this it is okay. I let it like this, better. H, O, H. This is the best method. See. Okay. Now, in this case, see, observe it now, tetrahedral. That is, each oxygen atom is tetrahedrally surrounded by 4 hydrogen atoms, in which 2 hydrogens are linked through the hydrogen bonds. This is hydrogen bond, again this is hydrogen bond, and whereas 2 more hydrogen atoms are linked through the covalent bonds. This is a covalent bond, even this is a covalent bond here, and this leads to the formation of open honeycomb structure, open honeycomb structure, or you may consider it as a cage-like structure, cage-like structure. That is, this cage-like structure consisting of space between the molecules. See, this is the space between the molecules. Due to the existence of the space in ice, the density of ice is always less compared to that of water. Hence, always ice floats on water. Okay. Now, let us consider the ammonia and also phosphine. Even in case of ammonia also, see, hydrogen, hydrogen, hydrogen. Nitrogen atom of one ammonia molecule, nitrogen atom of one ammonia molecule is linked to hydrogen atom of other ammonia molecule through intermolecular hydrogen bonding. This intermolecular hydrogen bonding is responsible for the high boiling point of ammonia when compared to phosphine, because in case of phosphine, say, hydrogen bonding is not possible because hydrogen is linked to the less electronegative phosphorus atom. And in this again nitrogen and you take up phosphorus, both belongs to the same group, and hydrates of both are expected to have the same properties, but they do not have with respect to this. Okay. That means ammonia having higher boiling point compared to phosphine. Then you consider one more, that is called as intramolecular hydrogen bonding. Intramolecular hydrogen bond means here intramolecular hydrogen bond, that is intramolecular means within the molecule of the same substance. Hydrogen bonds formed within the molecule of the same substance is known to be intramolecular hydrogen bonding. That is, you can consider example, that is orthonitrophenol. See, this is orthonitrophenol, this is phenol, orthonitrophenol, N double bond O, and this is coordinate bond. Now this type of bonding is called as the intramolecular hydrogen bonding. That is hydrogen bond formed within the molecule of the same substance. In orthonitrophenol, hydrogen atom is linked to the oxygen atom, so it is called as intramolecular hydrogen bonding. And suppose if you consider the paranitrophenol, see, in case of paranitrophenol, OH, now NO double bond O. In case of paranitrophenol, so intramolecular hydrogen bonding is not possible, where intermolecular hydrogen bonding is possible. Okay, that is with reference to the hydrogen bond. Now let us consider the most important one, that is known to be lattice energy. Now lattice energy means the energy required to break 1 mole of an ionic solid into its respective gaseous ions is called as lattice energy. That is, you consider sodium chloride, which is a solid. It dissolves. If you want to break it into respective gaseous ions, some energy is required. That is Na plus gas plus Cl minus gas. Now it is generally represented as U. It is always negative because energy is required to break the molecule into respective gaseous ions. Now remember lattice energy. Okay. I will write Le here. Remember, stability of the compound is directly proportional to lattice energy. Higher the lattice energy, more the stability of the compound. And whereas suppose if we take up the lattice energy in case of the alkali metallic halides here, lithium, sodium, potassium, rubidium, cesium, and also francium. Now for a given halogen like X, LIX, whichever may be the halogen being the same, now the lattice energy from top to bottom decreases. Lattice energy decreases means here LIX having more lattice energy compared to sodium halide, compared to potassium halide, compared to rubidium halide, okay, compared to cesium halide, when compared to francium halide, if forms. Okay. That means totally from top to bottom lattice energy increases for a given halogen. That is with reference to the lattice energy. And even suppose if we consider for a given metal, if it is a lithium fluoride, then lithium fluoride, lithium chloride, lithium bromide, and lithium iodide. in such a case the lattice energy of lithium fluid is more compared lithium chloride, compared lithium bromide, compared lithium iodide. That means as atomic radius increases, automatically lattice energy decreases. That is with reference to lattice energy. Now suppose if we consider the types of covalent bonds, it is there types of covalent bonds. You know about the types of the covalent bonds. One is called as sigma bond. Types of covalent bonds. Types of covalent bonds. One is called sigma bond and one is called as pi bond. Now it is sigma bond, first one. You know sigma bond, it is a chemical bond formed by the direct overlapping of two half-filled atomic orbitals. That is, there are different types of sigma bonds. It is S sigma bond, that is formed between two s orbitals like this. Okay. Then secondly it is sp sigma bond, that is one is s orbital and one is the p orbital. Direct overlapping takes place to form a sigma bond. And one more is called pp sigma bond. In case of the pp sigma bond, see here, one is the p orbital, other is also the p orbital. It is the pp sigma bond. And suppose if you consider the formation of pi bond, that is pi bond. A pi bond is always formed by the lateral or sideway overlapping of two half-filled atomic orbitals. It is like this. See. Now you can consider this is actually called as the pi bond. Always sigma bond is stronger when compared to the pi bond, because the extent of overlapping in case of sigma is more compared to the pi bond. That is with reference to a brief idea about the covalent bonds here. Now we have to consider the most important concept, that is known to be hybridization. This is usually, as per my knowledge, many times there were questions based on this hybridization. Okay. Let us consider, let us give importance for this hybridization, very important hybridization. Okay. Now what is hybridization? The phenomena of reshuffling of orbitals and redistribution of energy among the orbitals to form new orbitals of similar shape, similar size and equal energy is known to be hybridization. That is, for example, if one s orbital hybridizes with one p orbital, now two sp hybrid orbitals are formed. When one s orbital hybridizes with one p orbital, two sp hybrid orbitals are formed, in which the bond angle is 180 degrees and shape of the molecule is linear. Linear is the shape of the molecule. That is just a brief hint about it. It is s orbital, this is the p orbital. Now reshuffling may be represented like this. Okay. Reshuffling of orbitals and two orbitals, that is one is like this, one is like this, and if you combine both of them you can write it like this. Okay. This is the bond angle, it is 180 degrees. And now you consider one beryllium chloride as an example here, beryllium chloride. In case of beryllium chloride, see Be, Cl and Cl, linear shape it has. Then one more, if one s orbital hybridizes with two of the p orbitals, it gives three sp2 hybrid orbitals, three sp2 hybrid orbitals. Now among these three sp2 hybrid orbitals, they are arranged at three corners of a triangle. That is bond angle is 120 degrees and shape of molecule is trigonal planar. Trigonal planar. Trigonal planar is the shape of the molecule. Now example you can consider BCl3, that is boron trichloride. That means BCl Cl, Cl. Okay. Now, one more you consider, that is a sp3 when one s orbital hybridizes with 3 of the p orbitals, 4 sp3 hybrid orbitals are formed, in which the bond angle is 109.5 degrees and the shape of molecule is tetrahedral. Shape of molecule is tetrahedral. Now we consider methane CH4 for this, which you can write as C H H H H like this. That is a tetrahedral. Okay. Now let us consider some other points here. That is when one s orbital hybridizes with, it is a fourth one I think, one s orbital with one p orbital, 3 p orbitals and with one d orbital, it is called sp3 d2. It is sp3 d2 hybridization, and it is sp3d hybridization. That means in which, see here, the shape of molecule is trigonal bipyramidal and bond angle is 120 degrees and also 90 degrees. Shape of molecule is trigonal. Okay. It is bipyramidal. Trigonal bipyramidal. Okay. That is we can consider PCl5 as the example here. PCl5, phosphorus pentachloride. See, which may be written like this. Okay, phosphorus. Now this is 120 and this is 90. PCl5. Trigonal bipyramidal. And one more you consider, that is when one s orbital hybridizes with 3 of the p orbitals, and 2 of the d orbitals, it is sp3 d2. sp3 d2, in which the bond angle is 90 degrees and example you can consider, the shape of molecule is the octahedral. And here, see, example we can consider sulfur hexafluoride SF6. I'll write it here. See, you can write octahedral shape like this. S 1, 2, 3, 4, 5, 6. SF6. This is octahedral shape. Now we take up one more. That is 6, 1. When one s orbital hybridizes with 3 p orbitals and also 3 d orbitals, it is called as sp3 d3. That means totally 7 hybrid orbitals are formed there. That is so in which the bond angle is found to be, see, shape of molecule pentagonal bipyramidal. Pentagonal, it is bipyramidal. Pentagonal bipyramidal, and bond angles are 90 degrees and also 72 degrees. That is which you can write like this. See, example IF7. Iodine heptafluoride. It is iodine 1, 2, 3, 4, 5. It is like this. Iodine heptafluoride. Okay. It is iodine heptafluoride. This is brief account regarding the hybridization. But if they give the molecule, for example, they will give SF6, how to find the hybridization? They will give SO42 minus, how to find the hybridization? Now, let us consider the technique with respect to it now. How to find the hybridization? To the maximum extent we can use it. See, let us consider some molecules also here. That is, now I will write N is equal to half into VMCA, V plus M minus C plus A. Let us know what is this V, M, C and also A here. That is again I will write one more, L, that is N minus M minus D. L means number of lone pairs. This can be used to find the hybridization and also can be used to find the number of lone pairs of electrons. Now here N is called number of hybrid orbitals, number of hybrid orbitals, and then V is the number of valence electrons, number of valence electrons, and then M is number of monovalent atoms, number of monovalent atoms, and then C is number of positive charges, and then A is number of negative charges. Now L is number of lone pairs, and whereas D is number of bivalent atoms, Now let us find the hybridization in this case here. I will take up some molecules here, that is let us consider the molecules. First I will take water, then ammonia, then sulfur trioxide, and then it is I will take up the molecules having some positive charges, that is NH3 plus and then H2O plus, and let us consider some molecules having negative charges also, that is SO4 2 minus and ClO3 minus, some molecules. Okay, now let us consider here. I will take up the ammonia or water and also sulfur trioxide first. Now I will take up ammonia molecule. In case of ammonia, the central atom is nitrogen. Nitrogen contains 5 valence electrons. Number of valence electrons in nitrogen is 5 because atomic number 7, 1s2, 2s2, 2p3. Apply the formula here. N is equal to N half into V. What is V? Number of valence electrons. How many valence electrons are present there? 5 minus M. Number of monovalent atoms. Number of monovalent. How many monovalent atoms are there? 3. 5 plus 3. How many positive ions are there in ammonia? No positive ions. So it is 0, minus 0. Any negative charge on ammonia? No. It is again 0 only. So totally half into 8, that is equal to 4. Let us consider number of hybrid orbitals here. Now based on the number of hybrid orbitals, you can find the hybridization. That is here I will give an idea about it. See, N, if it is 2, 3, 4, 5, 6, 7. Type of hybridization will be, if it is 2 sp, 3 sp2, okay. If it is 4 sp3, 5 sp3 d6 sp3 d2, 7 sp3 d3. Okay. Now number of hybrid orbitals is 4. So the hybridization in case of ammonia is sp3. What is hybridization? sp3. If hybridization is sp3, what is the expected shape? Tetrahedral. And what is the bond angle? 109.5 degrees. That is expected. Really, we can discuss with respect to VSCPR theory. And then, like that, you consider even for water molecules also, for water. And in case of water oxygen, atomic number 8, electronic configuration 1s2, 2s2, 2p4. So, how many valence electrons are present in this? 4 plus 2, 6 valence electrons are present here. Now, here it is n is equal to half into 6 valence electrons, that is V is 6. Number of monovalent atoms 2. Okay. Number of positive charges 0 plus number of negative charges 0. That is totally it is half into 6 plus 2 8, totally 4. Again hybridization is sp3 because see 4, number of hybridizers is 4, so it is referred to sp3 hybridization. If sp3 is hybridization, what is the expected shape? Tetrahedral. What is the expected bond angle? It is 109.5 degrees. Okay, really it is not 109.5 in case of water. That can be explained based on the VSCPR theory in the next concept. Okay, that is with respect to this. And now, suppose if I consider the next molecules having positive charge, it may be NH3 plus. Okay, and also let us find the number of valence electrons in that case. Say now, suppose if we take up NH3 plus, okay, now NH3 plus, NH3 plus, again n is equal to half into number of valence electrons. Let us take up NH4 plus, better, NH4 plus, that is NH4 plus. Now, in this case half into number of valence electrons in nitrogen is 5 plus number of monovalent atoms 4 minus number of positive charges 1 plus number of negative charges 0. Totally 5 plus 4, 9 minus 1, 8, 8 by 2, that is again 4. So, expected hybridization is sp3, sp3. Okay. So, expected bond angle is 109.5. Expected shape of molecule is tetrahedral. And here you find the number of lone pairs. L is equal to n. What is n? Number of hybrid orbitals. How many? 4. Minus m. Number of monovalent atoms. How many? 4. Minus no bivalent atom here. It is 0. So 0. Number of lone pairs of electrons in H4 plus is 0. Okay. And it has a shape of tetrahedral. Now, one more you consider. Like that you can even find for the SO4 2 minus also and H2O plus also. Now, one example will take up with respect to SO4 2 minus here. That is in case of SO4 2 minus sulfur, again sulfur, you consider SO4 2 minus sulfur. So, how many valence electrons in sulfur? Oxygen sulfur belongs to the same group. Sulfur atomic number 16, it is 1s2, 2s2, 2p6, 3s2, 3p4, 6 valence electrons in sulfur. Now, it is n is equal to half into number of valence electrons is 6 plus number of monovalent atoms. There is no monovalent atoms in case of sulfate ion, containing only bivalent atoms. Number of monovalent atoms will be 0 minus number of positive charges 0 plus number of negative charges 2. So, it is 6 plus 2 8, 8 by 2, that is again 4. So, it is hybridization is sp3. sp3 is the hybridization. And here you find the number of lone pairs of electrons. L is equal to, what is L here? N minus M minus D. L is how much here? 4. N is 4 minus, no monovalent atoms. So, minus bivalent atoms is 4 0. No lone pair of electrons. That means one thing remember, if the given molecule does not contain any kind of lone pair of electrons, then no doubt the expected shape is exactly equal to the real shape. If there is lone pair of electrons, there will be distortion that we can consider based on the VSEPR theory, that is a valence shell electron pair repulsion theory. And then you consider one more example if you want. Okay. Now, let us consider the VSEPR theory, that is valence shell electron pair repulsion theory. Now, what is this VSEPR theory? Now, actually, according to VSEPR theory, we have to discuss importantly about water and also ammonia. According to VSEPR theory, valence shell electron pair repulsion theory, the lone pair repulsion is more compared to lone pair bond pair repulsion, which is again more compared to bond pair repulsion. This is according to VSEPR theory. Okay. Now, let us apply this VSEPR theory to molecules like ammonia and also water here. That is, I will take up water molecule, water and also ammonia molecule. In case of ammonia or water, expected hybridization is sp3. sp3 is the expected hybridization, and whereas the expected shape, this is expected, I am writing, expected shape of molecule is that means structure or geometry we can consider. Expected geometry is tetrahedral. Okay. And expected bond angle is bond angle. Expected is 109.5 degrees in both. But actually, in case of this water molecule, in case of the water molecule, see, that is correct bond angle is 104.5 degrees. That is expected hybridization in case of water is sp3, and even in case of ammonia also sp3. And expected geometry is tetrahedral. In both, expected bond angle is 109.5 degrees. But water contains 2 lone pairs of electrons, and whereas ammonia contains 1 lone pair of electrons, which you can write H, O, H. These are the 2 lone pairs of electrons present on oxygen atom, and in case of ammonia, it contains 1 lone pair of electrons. Okay. Due to the presence of 1 lone pair of electrons, the bond angle decreases from 109.5 to 107 degrees. 109.5 to 107 degrees. Hence, the correct shape of ammonia is pyramidal, but not tetrahedral. And whereas in case of water molecule, due to the presence of 2 lone pair of electrons, the lone pair repulsion, which is more compared to lone pair compared to bond pair, bond angle decreases from 109.5 to 104.5 degrees. Hence, The correct shape of molecule is bent. Water has bent shape and ammonia has a pyramidal shape. You can write the pyramidal shape like this. See, one lone pairs, hydrogen, hydrogen and hydrogen. Whereas the water, which you can write as that is O, H, H, and there are two lone pairs of electrons. That's all regarding it. That is according to VSCPR theory. Now let us consider some questions, and while answering the questions, while discussing the questions itself, we can take up the molecular orbital theory. Now let us consider some of the important questions here. Okay, that is see, first question, an ionic compound A plus B minus is most likely to be formed when A, the ionization energy of A is high and electron affinity of B is low. B, both ionization energy of A and electron affinity of B is low. Both C, both the ionization energy of A and electron affinity of B is high. D, the ionization energy of A is low and electron affinity of B is high. See, for this question, usually ionic bond is formed between alkali metals or alkali earth metals and with halogens. Here alkali metals or alkali earth metals will have low ionization energy and the combining halogens will have high electron affinity. Hence, option D is the correct answer. Option D. Okay, next question. That is say second one. The ammonia has higher boiling point than expected because it forms ammonium hydroxide with water. Its density decreases of freezing. It has strong intermolecular covalent bonds. It has strong intermolecular hydrogen bonds. You know it is due to hydrogen bonding. So option D is the correct answer. See, question number 3. In BCl3, the hybridization state of boron is sp, sp3d, sp3, sp2. You know how to calculate, that is using the formula, that is BCl3, boron trichloride. In this case, the formula to be used is N is equal to half into V plus M minus C plus A. Now, boron atomic number is 5, electronic configuration 1s2, 2s2, 2p1. See, outermost orbit consisting of 3 electrons. 3 electrons are present in boron. That is see, boron that is 1s2, 2s2, 2p1. Okay, 3 electrons, half into number of electrons, valence electrons in boron is 3 plus number of monovalent atoms, 3 chlorine atoms are present, so it is 3 minus, it does not contain any positive or negative charge, number of cations is 0, number of anions is 0, totally it is 6. So half into 6, that is 3. So 3 hybrid atoms are present. If 3 hybrid atoms are present, N is equal to 3. So hybridization is sp2. 1 s orbital with 2 p orbitals. So A sp, B sp3d, C sp3, D sp2. Correct option is sp2. That is D. D is the correct answer. Now the fourth question. The type of bonds present in ammonium chloride are very simple. Already we have discussed it under the synopsis. See, if you take up the ammonium chloride, in case of ammonium chloride, NH4Cl, see, which may be even written like this, NH3, okay, HCl. So it contains, it may be written even like this, NH4 plus Cl minus, means it contains positive and negative charge. So ionic bond is present. And if you consider ammonia, ammonia consisting of covalent bonds, and then even it contains coordinate bond also, that is you can take up the options only covalent, only ionic, coordinate and covalent, ionic, coordinate and covalent. D is the correct answer. Okay. Now the next, the bond angles in molecules H2O, NS3, CH4 and CO2 are in the order. Now to find the bond, that means bond angles, what we can do is you just find the hybridization. Now if you consider hybridization, in case of water it is sp3, and in case of ammonia it is again sp3, in case of methane also it is sp3, and whereas in case of carbon dioxide it is sp hybridization. And that is suppose if you consider water, the bond angle in water is 104.5 degrees, and in case of ammonia it is 107.5 degrees, and in case of methane it is 109.5 degrees, and in case of carbon dioxide it is 180 degrees. Okay. Based on this, what we can consider is C. So least is water H2O having less bond angle compared to ammonia, okay, compared to methane, then compared to carbon dioxide. So the correct option is D. H2O less than NS3 less than CH4 less than CO2. D is the correct answer. Next, the ion that is isoelectronic with COEs. Let us consider the isoelectronic ions. Isoelectronic ions means ions having same number of electrons are called as isoelectronic ions. Now you just count the number of electrons. In case of oxygen, O2 minus, that is oxygen, atomic number is 8. 8 into 2 oxygen atoms, that is equal to 16, plus 1 negative charge is there, 1, that is 17 electrons in O2 minus. And whereas in O2 plus, that is 8 into 2, 16, due to the presence of positive charge you can remove 1 electron, that is subtract 1 electron, so it is 15. Okay. And whereas in case of N2 plus it is 7, atomic number is 7, 7 into 2, 14 minus 1, that is 13 electrons. And in case of Cn minus, carbon 6, nitrogen 7 plus 1 electron, totally 14 electrons. Now we count number of electrons in carbon monoxide. Carbon 6, oxygen 8, that is 14. Remember, that is 14. So option D is the correct answer. Cn minus. CO is isoelectronic with Cn minus. Option D is the correct answer. Now, which of the following hybrid orbitals has highest S character? Now, how to calculate percentage of S character here? That is percentage of S is equal to number of S orbitals, divided by total number of orbitals, into 100. Now we calculate for sp3, it is in sp3 it is 1 s orbital divided by total number 3 plus 1, 4 into 100, that is 25%. And sp3d b, that is A, B is sp3d, 1 s orbital divided by total number of orbitals will be 1 plus 3, that is 4 plus 1, 5, totally 1 by 5 into 100, that is 20%. And whereas C, that is D sp2, 1, 2, 3, 4 orbitals, 1 s orbital into 100, now it is again 25%. And one more, that is D sp2 d 1 s orbital that is divided by how many? 2 plus 1 3 okay, into 100, that is 33.3%. 25%, 20%, 25%, 33.3%, that is totally D is the correct option. That is sp2 has higher percentage of S character. One more thing, remember, increase in S percentage of S character decreases electronegativity. That is electronegativity is inversely proportional to percentage of S character, percentage of S. That is lower the percentage of S character, higher the electronegativity. Okay, now hence why Sp is more electronegative compared to Sp2 compared to Sp3. So correct option is D here. Again, one more. The maximum possible number of hydrogen bonds a water molecule can form is, say, in case of water molecule, you can write number of hydrogen bonds H, O, H. Now, this oxygen can form 2 hydrogen bonds like this, and it is one more H, O, H, and it is this hydrogen can combine with one more oxygen with one more hydrogen bond. Again, this may also combine with one more oxygen with one more hydrogen bond. So totally 1, 2, 3, 4 hydrogen bonds are possible. So option D is the correct answer. Then see, both, next question, both BF3 and NF3 are covalent compounds, but BF3 is non-polar while NF3 is polar. Let us consider the reason. They have given atomic size of boron is smaller than that of nitrogen. Nitrogen is more electronegative than boron. BF bonds have less polarity than NF bonds. BF3 is planar, but NF3 is pyramidal in shape. C, that is boron trifluoride. This is boron trifluoride. The shape is triangular planar. Okay. Whereas if we consider NF3, it contains a lone pair of electrons. Hence, it has pyramidal shape 1, 2, 3. So that is bond moments. We can consider both BF3 and NF3 as covalent compounds. Both BF3 and NF3 are non-polar, but BF3 is non-polar while NF3 is polar. This is the reason. That is BF3 is planar, but NF3 is pyramidal shape. Hence why the answer is D. Okay, D is the correct option. Now 10. A diatomic molecule is stable only when number of bonding and anti-bonding molecular orbitals are equal, number of electrons in bonding and anti-bonding molecular orbitals are equal, the bond order is 0, number of electrons in bonding molecular orbitals is greater than in anti-bonding molecular orbitals. That means actually they are asking about the stability. Remember, stability of a molecule directly proportional to bond order. Stability of a molecule is directly proportional to bond order. Now, higher the bond order, more the stability of the molecule. Then remember one more important point here, that is bond order. Bond length is inversely proportional to bond order. Lower the bond order, bond length, that is for example C single bond C, C double bond C, okay, and C triple bond C. It has higher bond length. C single bond C bond length is more compared to C double bond C compared to C triple bond C. what it indicates here, as the bond order increases, bond length automatically decreases. As the bond order increases, bond length decreases, means bond length is inversely proportional to bond order here. And one more important point here, diatomic molecule is stable only when they are asking bond order. How do you calculate bond order? Bond order is equal to NB minus NA by 2. If you want to get the positive bond order, NB must be greater than NA. NB must be greater than Na. What is NB? Number of electrons in bonding molecular orbitals. What is Na? Number of electrons in anti-bonding molecular orbitals. That is, from the answer you can consider number of electrons in bonding molecular orbitals is greater than in anti-bonding molecular orbitals. So, option D is the correct answer. Then, which of the following molecules is expected to be paramagnetic in nature? See, to find the magnetic nature, you people, what we can learn, what technique we can remember is, see, count the number of electrons. That is the number of electrons in the molecules. Which of the following molecules is expected to be paramagnetic in nature? See, number of electrons. If number of electrons are 1, number of electrons present in the molecule 1, 3, 5, 7, 9, 11, okay, it is 13, 15, 17, 19, okay. Then these are all paramagnetic, no doubt. Then if the number of electrons are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. In this case, except 10 and 16, these two are paramagnetic, remaining all are diamagnetic. Paramagnetic means slightly attracted by magnetic field, diamagnetic means repelled by the magnetic field. Now consider the option. Option A is given as nitrogen. Nitrogen means 2 nitrogen atoms, so that is 7 plus 7, that is 14. 14 is diamagnetic. Then B, hydrogen. Hydrogen 1 plus 1, that is 2. 1 plus 1 is 2. That is again 2, it is diamagnetic only. Then C, beryllium, Be2, that is beryllium atomic number 4, helium, boron, beryllium, okay, plus 4, it is 8, okay. You know hydrogen, then it is helium, lithium, beryllium, with the number 4 plus 4, it is 8. 8 is again diamagnetic only, diamagnetic, okay. Now you consider the next one, D, oxygen. Atomic number of oxygen is 8, okay. It is 8 plus 8, 16. With 16 electrons, it is found to be paramagnetic. That is option D is the correct answer, okay. Now, in which of the set of the species are all species paramagnetic, they are asking, okay. All the species are paramagnetic, they are asking, okay. Now just the same technique you can use, that is boron, B2, so 2 into 5, 5 is atomic number of boron, so 10 electrons. Then it is of oxygen, O2, it is option A, okay. Oxygen 8 into, that is 2 into 8, 16, that is again paramagnetic. And nitrogen, in case of nitrogen, it is 2 into atomic number 7, 14. So this is actually diamagnetic, paramagnetic, paramagnetic, okay. Now we take up one more, that is option B, in which B2 is paramagnetic. Now again O2, that is again paramagnetic, and you consider Li2, lithium, atomic number 3, 3 plus 3, 6, 6 is diamagnetic. Now, option C, again it is a B2, B2 is paramagnetic, F2, you consider F, 9, that is 2 into atomic number of fluorine is 9, so it is 18, 18 is again diamagnetic. Then oxygen, O2, O2 is paramagnetic, even that is not the correct option. Now you consider D here, in which B2, that is paramagnetic, okay. Then O2, that is also paramagnetic, and it is N2 plus, okay, that is N2 plus. Nitrogen, N2, 2 into 7, that is 14, plus means 1 electron to be subtracted, that is 13, 13 electrons is always paramagnetic, okay. That is B2 is paramagnetic, O2 is paramagnetic, and then N2 plus is paramagnetic. D is the correct option, okay. Now let us move to the next one. Now you know, like this you can calculate the bond orders and also bond lengths here. Now let us consider some questions based on the states of matter. See, states of matter. See, in case of states of matter, you have to refer Boyle's law, Charles' law, Avogadro's law, Dalton's law of partial pressures, then real and ideal gases, ideal gas equation, and then value of R in all the units, SI units, and also liter atmospheres, and also in calories. Then Van der Waals equation, compressibility factor, critical temperature, critical pressure, and also critical volume. As the timing running out, so let us concentrate on the questions only here. See, question number 27. For a given mass of a gas at constant temperature, if the volume of V becomes 4 times, the pressure will become, they are asking. See, this is a pressure volume relationship, and that is pressure volume relationship means Boyle's law. According to Boyle's law, volume is inversely proportional to pressure. Volume is inversely proportional to pressure. So based on this, you can consider PV is a constant. Now we can consider P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. Now for a given mass of a gas at constant temperature, temperature is constant, if the volume V becomes 4 times, suppose if you consider P1 as P, V1 as V, then if the volume V becomes 4 times, this becomes 4 times V, and the pressure P will become, they are asking P, they are asking you to calculate P2. Now we can cancel V, from this you can solve, you send it to the left hand side, P by 4, that is P2. That is answer D is P by 4. Option D is the correct answer. Okay. Now next one. Which of the following postulates of kinetic molecular theory of gas is not correct? Molecular collisions are perfectly elastic, that is correct. There are no forces of attraction or repulsion between molecules, even that is correct. The molecules are in a state of rapid motion in all directions, that is also correct. The average kinetic energy of the gas molecules is inversely proportional to the absolute temperature, that is wrong, because kinetic energy is directly proportional to temperature. Increase in temperature increases the kinetic energy. Okay. Now the option D is the correct answer. Option D. Okay. Now we consider which of the following molecules will have the highest RMSV at 27 degrees Celsius. Remember, you know, root mean square velocity, CRMS, that is equal to square root of 3 RT by M. Okay. With this, what we can consider is 3 is constant, R is constant, they are mentioning at a particular temperature 27 degrees Celsius. Hence why you can remember CRMS, that is inversely proportional to square root of m. That is a decrease in molar mass increases the root mean square velocity. Increase in molar mass decreases the root mean square velocity. That is, we find the answers NO2, and in NO2 atomic number of nitrogen is 7 and atomic mass of nitrogen is 14, plus for 2 oxygens it is oxygen atomic mass is 16, that is 2 into 16, totally it is equal to, now it is 14 plus 32, 16 to the 32, that is 46 B. That is oxygen. For oxygen it is 2 into atomic mass of oxygen is 16, so total it is 32. And for methane, see, it is for methane it is carbon 12 plus 4 hydrogens, each hydrogen atomic mass is 1, so it is 4, totally it is 16, totally it is 16. And whereas D, for hydrogen it is 2, so correct option is D. Lower the molar mass, higher the root mean square velocity. So option D is the correct answer, D. Okay, next. See the question number 30 in this case, that is for a given mass of a gas, if pressure is reduced to half and its temperature is doubled, then volume V becomes. For a given mass of a gas, if pressure is reduced to half and its temperature is doubled, that means it is a pressure temperature relationship, then volume you have to calculate. Okay, that is pressure, temperature and volume relationship. You know PV is equal to RT. You can write PV by T is equal to R, which you can write P1 V1 by T1 is equal to P2 V2 by T2. Now, for a given mass of a gas, from this you can write, if pressure is reduced to half, see, I will consider the pressure P1 as P, volume as V, temperature as T. If pressure is reduced to half, P2 becomes P by 2 into its temperature is doubled, that is it becomes 2T. Then they are asking me to find the V2 value. Then P gets cancelled, T gets cancelled. So from this you can write 2V by 2. So V is equal to V2 by 2 will come to the denominator. So which implies V2 is equal to 4 times V. Now answer D is the correct option. Option D is the correct answer. Okay. Now D. Next, see, this is a direct question. Compressibility factor. For ideal gases, PV is equal to PV by nRT is, that is a compressibility factor represented as Z here, equal to 0, greater than 1, less than 1, equal to 1, that is D is the correct answer. Remember, for ideal gases, for ideal gas, Z, compressibility factor is equal to 1, and if Z is greater than 1, the gas is less compressible. If Z is less than 1, the gas is expected to be more compressible. Okay. Now, the next the answer for that is D. The next question, critical temperature of a gas is the temperature, you know, critical temperature, critical pressure and also critical volume. What is critical temperature? The temperature above which a gas cannot be converted into liquid, that is below which it cannot be liquefied, at which 1 mole of it occupies 22.4 liters, at which it can be changed directly to solid, above which it cannot be liquefied. D is the correct option. That means you know about the critical pressure also. The pressure applied on the gas to convert 1 mole of a gas into liquid is called as critical pressure. What is critical volume? The volume of 1 mole of a gas at critical temperature and critical pressure is called as a critical volume. The answer for this is D. Okay. Now, see, this is one of the important questions. Hydrogen diffuses 6 times faster than the gas A. The molar mass of gas A is they are asking. You have to find the molar mass of the gas A. You know, it is according to Gram's law of diffusion. Rate of diffusion of a gas is inversely proportional to square root of its density. Based on this, you can write R1 by R2, that is equal to square root of D2 by D1. Okay, because you can consider it like this: R1 proportional to 1 by root of D1 and R2 proportional to 1 by root of D2. Now 1 you write, 2 you write, it is 2 divided by 1 implies R1 by R2 is equal to root of D2 by D1. And you know, density is equal to mass by volume, which implies density directly proportional to mass. And from this, R1 by R2 is equal to square root of M2 by M1. Okay. Now, they are asking question: hydrogen diffuses 6 times faster than the gas A. The molar mass of gas A. You want to find the molar mass of the gas A here. Hydrogen diffuses 6 times more times the gas A. Now what I will do is I will write hydrogen. Okay, and this is Ra, that is gas A, that is M2. Instead of here I will write Ma divided by 1 is hydrogen, that is mass of hydrogen, molar mass of hydrogen. Hydrogen diffuses 6 times than the gas A, that means it is diffusing 6 times more, that is R of H2 by R of A is 6 divided by 1, that is equal to square root of Ma divided by, what is molar mass of hydrogen? For 1 hydrogen it is 1, for 2 hydrogens it will be 2, that is 2 here. Now which implies the squaring on both the sides, 36, that is equal to, so Ma by 2, Ma by 2, squaring on both the sides, square root will be cancelled. Now it is 36 into 2, 36 into 2, that is equal to Ma, that is totally 72 is equal to Ma. Now answer is here 72. 72 means here D is the correct answer. Okay. Now you consider one more question here. Weight of 2 liters of nitrogen gas at NTP. Now you know gram molar volume. What is gram molar volume? 1 mole of any gas occupies a volume of 22.4 liters at STP. That is 1 mole of a gas occupies a volume of 22.4 liters at STP. Okay. Now they are asking the weight of 2 liters of nitrogen. You know, you find the molar mass of nitrogen. What is the molar mass of nitrogen? Molar mass of nitrogen, that is equal to, for nitrogen it is 14. So 14 plus 14, that is equal to 28. And it is for 28 grams. The volume is 22.4 liters. That is 22.4 liters. The mass is 28 grams. Then they are asking it for approximately, it is not up to 2 liters. So 28 into 2 divided by 22.4 is 11.2. 11 point means 2 point approximately 5. Approximately 2.5, it is 34. That is the answer D. D, that is 2.5 grams. Okay. Now you consider one more, that is question number 35. and in this case 160 ml of a gas are collected over water at 25 degrees Celsius and 745 millimeter of mercury. If aqueous tension at 25 degrees Celsius is 23.8 millimeter of mercury, then pressure of dry gas, see, pressure of dry gas, that is equal to total pressure minus aqueous tension. What is aqueous tension? Pressure due to water vapor is called as aqueous tension. Okay, that is 745 millimeter of mercury, 745 minus 23.8, it is around 721.2. So the correct answer is D. D is the correct answer. Okay, here. Now see, this again one more very important question, that is the temperature of a sample of sulfur dioxide gas is raised from 27 degrees Celsius to 327 degrees Celsius. The average kinetic energy of the gas molecules, you know, kinetic energy is directly proportional to temperature. Kinetic energy is directly proportional to temperature. Now the temperature is raised from 27 degrees Celsius to how much? 327 degrees Celsius. Okay, 27 means you convert into kelvins, 27 plus 273, that is 300 kelvins. Now it is increased from 300 kelvins to 327 plus 273, that is how much? 600 kelvins. See, remember the temperature is doubled, so kinetic energy is also doubled. Now see, D is the correct answer, because as the temperature is doubled, kinetic energy is also doubled. Okay, now see the next question, that is D is the correct answer. Root mean square velocity of sulfur dioxide gas becomes the same as that of methane at 27 degrees Celsius when the temperature is, you know, root mean square velocity CRMS directly proportional to, that is equal to square root of 3 RT by M. Based on this, they are considering root mean square velocities of sulfur dioxide and also methane, they are making it equal. Based on this, we can consider T1 by M1, that is equal to T2 by M2, because they are considering sulfur dioxide and also the methane. If we consider from this, you can derive this formula, T of sulfur dioxide by M of sulfur dioxide, that is equal to T2, that is of methane, T of methane divided by T of it is M of methane. Okay, now T at what temperature, that is root mean square velocity of sulfur dioxide gas becomes the same as that of methane, that is you have to find T SO2. You know molar mass of sulfur dioxide, how do you calculate? For sulfur it is 16, and for 2 oxygens it is 30, for sulfur it is 32, for sulfur it is 32, for 2 oxygens it is again 32, totally 64, that is equal to T of methane is given, that is 27 degrees Celsius, 27 plus 273, 27 degrees Celsius, that is 27 plus 273, so totally 300 kelvins. Now this is 300, okay, divided by molar mass of methane, it is 16, so 16 4s are cross multiply, T of SO2 becomes 300 into 4, that is 1200 kelvins. 1200 Kelvin means if you want to convert it into degrees Celsius, subtract 273, so it is 927 degrees Celsius. So correct answer is D here. Okay, that is with respect to the states of matter. Now let us consider some questions from the next concept, that is known to be the redox reactions. Okay. D. One more question. The heat capacity at constant volume of an ideal gas consisting of monoatomic molecules is 3/2R, where R is the gas constant. The heat capacity at constant pressure is, you know, Cp minus Cv is equal to R. You have to calculate heat capacity at constant pressure. Cp is equal to R plus Cv. R plus Cv is how much given there? 3/2R. So totally it will be 5/2R. 5/2R means option D is the correct answer. Okay. Now let us consider some questions from the next, that is redox reactions. And from redox reactions you just refer oxidation, reduction, redox reactions, calculation of oxidation number, types of redox reactions, combination, decomposition, displacement and also disproportionation. Now first one, oxidizing agent is a substance which loses one or more electrons, causes reduction to occur, itself gets oxidized, accept one or more electrons. That is, it accept one or more electrons, that is D is the correct answer. Now let us consider how to calculate oxidation numbers. This is important. Oxidation number of chromium in K2Cr2O7. See, K2, okay, Cr2O7. Now how to calculate oxidation number here? For potassium, oxidation number is 1. 2 potassium atoms are there. 2 into plus 1 plus, it is 2 chromium atoms are there. 2 chromium atoms. I will write 2x plus, how many? 7 oxygens are there. 7 into, what is the oxidation number for oxygen? It is minus 2. Totally it is a molecule. Sum of oxidation numbers is equal to charge present on the molecule. Charge is 0 here. Now from this you can write plus 2 plus 2x minus 14, that is equal to 0. Now 2x, 2 minus 14, 2x plus 12 is equal to 0. So 2x is equal to 12. Now it is 6. So x is equal to plus 6. So this is the method which you can use for the calculation of oxidation numbers. Now the next question, that is answer for this is oxidation number of chromium in potassium dichromate is plus 6. Okay, that is D is the correct answer. Now oxidation number of chlorine in Cl2O, Cl2, ClO3 minus is respectively. Let us know how the oxidation numbers can be calculated here. That is in case of Cl2O, in case of Cl2 and in case of ClO3 minus. Okay, Cl2O, that is chlorine 2x, for oxygen it is minus 2, that's equal to 0, so implies 2x is equal to 2, implies x is equal to plus 1. Okay, then for chlorine it is in the elemental state, oxidation number will be 0. And one more, it is ClO3 minus, x plus 3 into minus 2, that is equal to minus 1. So which implies x minus 6 is equal to minus 1. X is equal to 6 minus 1, that is x is equal to 5. So oxidation number of Cl2O is, in Cl2O is plus 1, then Cl2 is 0, Cl3 minus is plus 5. So option D is the correct answer. Option D. Okay. See here, if the formula weight of Cr2O7 2 minus ion is m, then in the reaction Cr2O7 2 minus plus 14H plus 6 electrons 2Cr3 plus 7H2O. The equivalent weight, how to find? Equivalent weight is equal to molar mass divided by how many electrons are involved there? So it is 6. That is m by 6. M is molar mass. So D is the correct answer here. Now let us consider one more. Okay. The oxidation number of lead in Pb3O4 is see, it is Pb3O4. Now it is for lead 3x plus 4 into minus 2 is equal to 0. Now it is 3x minus 8 is equal to 0, and it is 3x is equal to 8. So x is equal to 8 by 3. So correct answer is plus 8 by 3, means D is the correct option here. Students, we can stop here. All the best for your examinations. Study well. Okay, thank you.